So Lin-Manuel Miranda totally dropped the ball. Hamilton was awful because while U.S. history is certainly worth talking about, there is a better alternative musical. I see the scowl, but believe me, this is true. There's a much better story that could have been told in the form of a Broadway musical rather than Hamilton. Not that Hamilton was terrible, but what do you guys, who discovered calculus? Do you guys know?
No.
So when you think of physics, you probably think of two names, is my guess. You think of Einstein, which is a contemporary name in physics. Is there an old name, like 1600s old? Physicist from 1600s. John Calc is a good idea. Here I am just hanging out here, sitting in my front yard, being a young guy. What made that apple fall? Newton didn't make the apple fall, but I'm talking about Newton. Now, do you guys know anything about Newton, like what he did? What? So he discovered the Newton's laws of motion, sure. And he did that, why? So why not say reasonable? That's always a hard one to answer, and I'd never know the right way to respond. Yeah, because he felt like, I don't know how to answer that question. Okay, but looking at it, he realized that the math that existed was not good for doing physics, and it was really gross and terrible to work with. So rather than just trying to trudge through this all and deal with it, he said, what if there was a better math? And it turns out there is. He laid the groundwork for calculus. Now, at the same time, in Europe, a few hundred miles away, Isaac Newton lived in Cambridge, Massachusetts. Whoa, not Massachusetts. That was weird. Cambridge in the UK, in England. It happened during the pandemic, so he had a lot of time on his hands. When you imagine Isaac Newton being the professor discovering the laws of gravity, how old is this guy in your head? What's he look like? 40, 50, 60? I think of an old white-haired guy. So, I mean, human lifespan and life expectancy is a weird discussion because we'll get there on another day. He lived a regular human lifespan. But people, when are people most involved in the academic world? Like, what age people live at university, don't have families to take care of and all that? 20s, roughly, right? In his early 20s is when Newton was doing all of this. Like, that's when the major advancements in mathematics predominantly happen, because if you have a family, Newton didn't, so he didn't have to worry about that. But if you have a family and other responsibilities, then obviously the math that you do at work might fall a little bit behind. Okay, so he's early 20s. But here's where the whole wrap back to the musical comes. At the exact same time, like almost identical time, hundreds of miles away in Germany, there's another wonderful guy, Gottfried Leibniz, who was doing some mathematics and stumbled upon this wonderful field of mathematics called calculus as well. They both discovered it simultaneously, differently, and I think that wholeheartedly there should be a musical about their feud and about who created it, and I think it'd be cooler than Hamilton. Hamilton sucked. All right, what I do know, though, is that in 5.2, we are going to be talking about some properties dealing with exponents. Properties of exponents. All right, I'm going to give you guys, this is going to count as our brain break is going to be pretty chill because we're not going to do a ton of writing today. But I have a kind of philosophical question for you. It does not relate to curling, although I wish it did. Easy. Okay. For these properties of exponents, my first and big question for you is, what's the best way to do math if we don't memorize it? Like, and it's kind of open-ended rather than like talk with your groups. How do we do math and get all this stuff in our minds without pure memorization? Because I'm not a huge fan of memorizing, but I think you guys know some of these things. If I don't know how this works, 2 to the x times 2 to the y, and maybe I don't know how this works, how could we possibly figure this out without just me saying, oh, here's the rule? There's a question. How would we decide what happens with these exponents if I don't just give you the rule? I'm going to give you guys 60 seconds. How would you figure it out if you don't have the rule just ready and locked? Go. So you might try to add some stuff, and that seems reasonable. Now, there is a rule at play here, and I'm certain that some of you guys know it. Angel, I know that you know it because you saw it. Now, here's the cool part about it. I don't want you guys to approach math typically with just a bunch of stuff to memorize. That is not the right way to do math. Now, having some stuff memorized does help. I'm not going to lie. If you know the square numbers, it's easier to break down square roots. If you know the cube numbers, it's easier to break down cube roots and so forth and so on. But there's lots of situations where it doesn't just have to be memorization, and it shouldn't be. We're going to look at some properties of these guys, and we're going to jump right in, and I'm going to leave you guys a little bit of time to work, because rather than me saying just what these properties are, I want you guys to discover them and to make sense of them. So we have quite a few properties. Now, I'm going to leave this side of the board for scratch work. You should leave one piece of your notes or a piece of scratch paper for some scratch work. But we're going to get a bunch of properties out of here with exponents. So we'll just say let x and y and a, I suppose, be real numbers. Now, for those of you that are writing this statement, anybody starting to use the shorthand notation on your own while we take notes? Okay, so just to check, Michael, do you mind, because you did give me a nod, can I look at your page and put it up here? Can I see your shorthand? If no, that's okay. Okay, so just to check, and this is stealing a little bit of time and the efficiency side of it may disappear. I've not looked at it, so we'll hope that it's not like just a rude comment about me. That would be so terrible. Hey, love it. We have this shorthand, x and y and a be real numbers. Alternatively, Michael, that's really good. You could shorten it even more. X, y, and a are in the set of what? Reals. And we can save a little bit of writing. And it's not a ton. Yours is really good. Like, I like the shorthand. I would encourage all of you guys to shorten the notes a little bit, because whatever I write, you probably want, but it doesn't have to be word for word. So we have a bunch of real numbers. We're going to work out the following properties, and we're going to list them all, and we'll come back and we'll work them out. The first of these properties is going to be the product rule, which, just to show you guys, what that means is we're going to take something like we just saw, a to the power of x times a to the power of y. Now, we're going to get this rule out, but I'm not just going to give it for free. We are going to look at all these. We have the product rule, and I'll try to switch colors on each. After the product rule, and these are in no particular order, just so you know, we'll look at the quotient rule. Should they be the same thing? Why would they be the same thing? Ooh, quotient is divide, but dividing and multiplication, are they the same operation essentially? Can I multiply by something that means the same as dividing? Yeah, so they're essentially the same. They should be pretty similar properties. Good catch, Seabass. Okay, these ones get kind of ugly. The power of a power is the third property that we're going to see. And we'll work all these out together, or some of them out together. We also will cover the power of product. I don't know why that P isn't capitalized, but we're just going to let it roll. And if we did the power of a product, any other guess of what we might talk about the power of? Power of a quotient, good. Then only two more after this. And I know it seems like a lot, but again, we're trying to work out a way to not just memorize. We also need to make sure, that we're cool with the idea of a negative exponent. And the last one is super neat. It is the zero exponent property. Okay. So we have a bunch of them. Now, as we look at this list, there's 2, 4, 6, 7 of them. As we go through with your hands, if it takes both of them, cool. How many of these properties do you think you know off the top of your head, just from Algebra 1? It could be 1 of them, it could be 0 of them, it could be 7 of them if you think you got it. Out of curiosity, hold up some number of digits, 1 through 7, or 0 through 7 rather. Which one are you curious about? X to the, or A to the X to the Y. Okay, numbers, where are we at? So I see a 5, I see a 3, I see a 5, I see a 2, I see a 0. We're all over the place. That's awesome. Good. Okay, check it out. If you have them memorized already, cool. If you don't, cool. You don't have to. So for this one, I'm going to work this one out first. If we have a to the x times a to the y, some of you guys know how this works. Do you know any nice powers of any numbers? Like, what's the easiest number to take powers of? 1 is unique. I'm not going to say 1 because 2 is easy. Do you guys know some powers of 2? Do you know quite a few of them? Should we play a game of 2s real quick? All right, check it out. We're not going to get through everybody. I'm going to start with 2 to the 1, and I know that 2 to the 1 is what? 2. So the next person I point at, or the next person's number that I call, you have to give me 2 to the next power. So just to make sure, I'm going to call somebody random, but if I start at 2, the next person I call, they're going to give me 2 to the second power, which is 4. The next person is going to give me 2 to what power? The third, and we're just going to see how 2y can we be. So let's see here. Okay, I'll start with the hardest one. 2 to the 1 is 2. What do you think, number 6? What's the next number?
Wait, what did you say the first?
2 to the 1 is where I did. I said it's 2. 2 to the 2 then.
2 to the 2? 4.
4, good. What's the next number in our powers of 2's list, number 10? So we went 2 and then went to 4. What's the next one? Oh. Ooh, it's 8. How about after 8? What's the next power of 2, number 1? Who is 1? 16. And then all of a sudden there's an easy way to start doing these. If I look at the numbers 2, 4, 8, 16, you don't even have to think about powers anymore. Every next number you just multiply by what? 2. So if you double 16, we're now at 2 to the 5th, and 16 times 2 is 32. And 2 to the 6th is times 2 again, gives me, and times 2 again, times 2 again, again, 1024 again, again. Again?
No.
Okay, so we're not going to keep going forever, but we could, right? You guys have just given me a ton of powers of 2's. I don't even need that many. If I wanted to work out the product rule, what do you notice about these? Do they match? Okay, the bases match is the language that we're going to use. These are the bases of my exponential. So let's just do an easy one. If I tried to do 2 to the 3rd times 2 squared, does that look like this property to you? Okay, so let's work it out. What is 2 to the 3rd? 8 times, what's 2 squared? 4. Do we agree that this needs to be 32? So help me out here. We're going to work our way up to this. I know that it's 32. And maybe there's a relationship here. What's 2 to the 1? 2. 2?
4.
3?
8.
8. So we're just multiplying by 2. Again, the 4th power of 2 is 16. And the 5th power of 2. So what we just worked out without having to memorize it, because we knew that these were connected, this is the same thing as 2 to the power of 5. What does it look like happened with these exponents? It looks like they added. Could it be a coincidence that we saw this one time and it just magically worked? Probably not, but we can try again. What's 3 squared times 3 to the 1, do you think? 3 to the 3rd, theoretically. Let's check. What's 3 squared? 9. And what's 3 to the 1? And what's 9 times 3? And let's try it here. And we're just going to double check to see if this property holds. What's 3 times 3? Times 3? Hey, did it work? Holy cow. So if we want to generalize or abstract this idea, this simply becomes the same base, a, to what power? The x plus y. Okay, if they have the same base, we apply this property. For the quotient, and we're going to go through, and this is likely going to be your assignment this evening to tack on, or in class maybe. How do you think we're going to write the general rule of the quotient? A to the x divided by a to the y. Does anybody feel confident that you know this power rule? If you don't, how could we work it out? How could we use a brief, easy example to make this more generalized idea work nicely? Can I use powers of 2 here? Yeah, give me a power of 2. I don't care what it is. 2 to the... I'm going to pick something bigger up here for no particular reason. Let's do this. 2 to the 4th over 2 squared. What's 2 to the 4th? Okay, don't guess. 2 times 2 times 2 is... we should know some of them. 16. Over what's 2 squared? And what's 16 divided by 4? Try again. Is that a power of 2? That's 2 to what power? So somebody right away said they subtract. Is that seemingly what happened?
Yes.
So how do we generalize this? A to the x over a to the y must be a to the power of x minus y. Love it. Okay, I'm going to give you guys these ones, and I'm going to give you a couple minutes here to work out the same thing. Use scratch work if you have to. I would use powers of 2. That's the easiest in my head. I would avoid 2 to the 1 and 2 to the 2 because it's a weird coincidence that 2 squared is the same as 2 times 2, and I try to avoid that. Okay, power of a power. Anybody think they know what I might write in here? A to the x, and all that gets raised to the y. Okay, what about the power of a product? And we're going to have to sneak in another real number here. And I'm going to sneak this in, and I should have had one more number. What happens if I take a times b to the x? Or what happens if I take, and I'll switch colors here, a over b raised to the x? Okay, these are the 5 most basic. 5, yeah. The 0 one, we may be okay with. What's anything to the 0? 1. So we're just going to commit to that one. A to the 0 equals 1. I'm going to make a caveat here. A has one restriction. It can't be 0. 0 to the 0 doesn't mean anything. Not for us. Okay. The negative one we will work out. I want you guys to spend the next 3 minutes, or the last 3 minutes if you will. Get me some scratch work. You probably have some of these memorized. I want you guys to give me the generalized rules for power of a power, power of a product, and power of a quotient, playing around with the scratch work if you don't know it. Cool. If you do know it, I would encourage help your classmates. And if you're not comfortable with this, I'm going to leave a hint for the negative one on the board. The rest of the time is yours to get the rest of the properties. So without talking, I'm going to give you a hint for how we do the negative. So you guys can not just watch me write stuff. I want to hear you guys chatting to get these properties. Up on the board is a hint for these.
I think from what I remember,
Cool. We'll pick up here tomorrow. You guys get the next 2 minutes to work out these props.